Hello. Hi, everyone. Already 4 people in chat. That's awesome. We're going to wait a few minutes before we officially begin, as usual. Already 4 people in chat. That's awesome. Hi, Christian. Well, 11 people now. Okay, so the sound seems all right. I'm just going to close the phone. Okay. How's everyone doing? So today I'm going to continue discussing the outer measure. Hopefully we'll do some exercise. And we will introduce the notion of sigma algebra. So finishing the properties of outer measures as well as introducing the sigma algebras are priorities. Hopefully we'll do that because this we'll complete those because even though the goals sound quite modest, right? But it's still, I would say, not the easiest thing to do because there are some highly non-intuitive results that we need to cover. And in the meantime, we also need to review a theorem in basic real analysis. Elementary real analysis, that's the Heine-Barreal theorem. Once again, in elementary real analysis, that's not a trivial statement at all. So we hope to cover all those things as well as do some exercise. So the workload is quite heavy. We wish to, last stream was 5 hours, right? So I wish to complete. We'll do the best we can. Okay, I'll do another 5 hours today, and in the meantime, I will minimize digressions. So yeah, I will try to focus as much as possible to only the material that is related to measure theory. Okay, because this is truly something that requires our full attention. This is not something that you can study passively and perhaps chatting over other topics like book recommendations and that sort of thing. So I apologize in advance if I can't answer those questions in this stream, in this series of streams actually. So Tuesdays streams are going to be very highly concentrated on just the subject matter. Because this is quite a dense subject and there's a lot of topics to cover. I'm not saying we will finish all of the book. Okay, I'm hoping to finish the majority of it, but I cannot guarantee. Okay, and there's probably going to some nonlinear reading as well. No audio? Hang on. No audio? I heard it on my phone. It was okay. Okay. Fosgel removed the message, so hopefully it's okay now. Okay. Okay. There's audio. Okay, great. Awesome. So that's the idea. So I apologize not being able to answer answer questions that aren't directly related to the main subject. Okay. Okay, great. So why don't we just get started? So last time we introduced the notion of an outer measure. So let's briefly review the definition of that. Okay, so our objective, first of all, our objective is to introduce a notion of size for the subsets of real numbers. Okay, and so imagine we're considering subsets of the real line, and we want the size or the length, right? The size of that we wish that our desired notion of size recovers the usual length. Right? So first of all, we have the definition of a usual length. Right? This is highly intuitive. If it's a bounded interval a to b, we're using open intervals, then the length is simply b minus a. Okay? If it's empty set, then the length is 0. If it is infinite or semi-infinite intervals, then the length will be infinite. So we're working with the extended reals here. So the length, and by extension the outer measure, takes values in the set extended real. So that's the notion of length. So whatever definition we come up with for the size of a set A, it should recover the length. Can you say hi to Angel Hannah, please? You recommended me. Hi to Angel Hannah. I don't know that person, but thank you very much for recommending my channel. Thank you very much, guys. So, so this is our first attempt to define the notion of a size for a general subset of real. Okay, it's called the outer measure. A bit of a spoiler. This turns out to be not a success. Okay, the notion of outer measure is useful. However, it fails to behave the way we want it to behave in certain critical circumstances. But still, nevertheless, this is a useful notion, and we will continue on discussing this notion. And there's actually something very deep about why notions such as outer measure fail to be a measure. Okay. So, without further ado, the definition of outer measure is an intuitive one. So, what we're really considering is covering an arbitrary set A. So let's say this is an arbitrary set A, which I visualize as an interval. Okay. In general, it doesn't have to be. For example, A can be the set of rational numbers, can be the set of irrational numbers, or can be some weird set that aren't intervals. Okay. What we're going to do is we're going to cover this set A by countably many open intervals. We're going to cover the set A using open intervals. So by a cover, we simply mean a collection of open intervals whose union contains A. So imagine I1 is like this, I2 is like this, I3 is like this. There might be overlaps between those intervals, I1, I2, I3, and so on. Okay, but the only requirement is that their union, this countable union, the union of all of them covers A or contains A. Now that's why this is called a cover. Okay, this is called a cover of open intervals of A. And then we're just going to calculate the total length of all those open intervals, which is this infinite series in general. And then we consider the set of all the possible sums of such infinite series and take the infimum. Why do we take the infimum? Because we wish to cover A as efficiently as possible. So you see, the picture I'm drawing here is not the most efficient one. Because, for example, you see I1, there is a portion that sticks out of from the left. Right? So this portion is simply unused. You can trim that, okay, and make the length a little bit shorter. Right? So in this process, we're essentially just taking more and more efficient covering of A and calculate the infimum of the total length. So that's something that we define as the outer measure. In the last stream, we discussed why this notion is well defined. Waited for that stream for so long. Hi, Andre. So yeah, thank you very much. I remember you from the last stream. So because I have other duties, okay, I upload and I have streams on other topics, so it's hard to be a one-man department. Okay, doing measure theory once a week is already my limit. It's already my supremum. Okay, so I apologize. You have to wait for that long. Okay, so that's definition of outer measure, and immediately we can prove a few basic properties. First, there's so-called good properties. First, countable sets have an outer measure of 0. Okay. And actually, there's even more basic statement. Finite sets have outer measure 0. Okay. So finite sets have an outer measure of 0, and countable sets have an outer measure of 0 as well. And the way we prove countable measure, prove that the countable sets have outer measure of 0, is very interesting. So essentially, we're just abusing the Zeno's paradox. Zeno's paradox. So what do we mean by that? So we're abusing the convergence of geometric series. Because you have a countable set, we're going to cover the set in such a way that the total length is a convergent series multiplied by a arbitrarily small number epsilon. So this way, the total length can be squeezed to as small as possible. Okay. So here we use the radius epsilon over 2 to the k for the interval ik. So ik covers ak. The ik covers ak, so this way all the elements in big A is covered. And then you just add all the lengths together, which is of course a geometric series that is convergent and is proportional to epsilon. So you just set epsilon tends to 0, basically because epsilon is an arbitrary small number, then the infimum is 0. Okay. It's a very classic trick in measure theory. All right, so let's continue. Outer measure preserves order. This is something we proved. Suppose you have A being a subset of B. So B contains A, then the outer measure of A must be less than or equal to the outer measure of B. So this is also what we say in probability theory called a monotonicity. Monotonicity. Okay. So if a set is contains another set, right, then the bigger set should have bigger measure, outer measure. Right, here's outer measure. We haven't even defined what a measure is now. Okay, we haven't defined what a measure yet. Okay, so I don't think we will be able to do that today, but we're getting there. Okay, and then we have this property about translation. So first of all, t plus a, this notation, t plus a is simply the set A translated by the unit of t. So t plus a, the set t plus a, is defined as the elements of t plus little a, where little a is in big A. Okay, and the next property says outer measure is translation invariant, which is again very nice. But it is our intuition that the size of the notion should not depend on the location of the set, right? So if you have a set and you measure its size and then you shift it by a certain unit, you shouldn't change the notion of size. Otherwise, it's highly non-natural. We don't want that to happen. So this is something that we liked. Okay, and I think it is a good exercise to prove it as an exercise. Okay, we will first read it and we'll write it in our own language in a perhaps 2-column format as an exercise, just as a warm-up. Okay. Suppose I1 all the way to I2 is a sequence of open intervals whose union contains A. Okay, so here we start with a cover of open intervals for A. Okay, who is Angel Hannah? Is that a fellow YouTuber? By the way, who's Hannah? Is 2 people already mentioned this name. Let me just search it up. Is that a fellow YouTuber? Okay. Sorry, I said about minimizing digression, but this seems important. If so, I should reach out to that person. And Johanna, I can't find it. Okay, apparently it's not a YouTuber, but it doesn't matter. Okay, so if you guys wish to share some information about this person and Johanna, then please let me know in chat, because I haven't heard about him or her. It's a him, right? Okay. So here we have the setup. Okay, we have, let's give ourselves a collection, a countable collection or a countable sequence of open intervals whose union contains A. And of course, shifting all those open intervals by T will cover T plus A. Okay, so therefore, the outer measure of T plus A must be less than or equal to the sum of the total length of T plus I1, T plus I2, and so on. Remember, the outer measure is the infimum among all such sums. Okay, and we have a property that is shown here in line. Here we have a property that is shown in line. So the shifting an interval does not affect its length. So L of T plus IK equals L of IK. Okay, so this says the outer measure of T plus A is less than or equal to the sum of the length of IK. But because the IKs is an arbitrary sequence whose union covers A, whose union contains A, this means if we take infimum on both sides of this inequality, okay, if we take infimum on both sides of this inequality, we get T plus A outer measure less than or equal to A outer measure. Okay, so we have one direction. So we have one direction for this inequality, so for this equality. Okay, this is a classic trick in analysis. Okay, something that is very common. Basically, in analysis, to prove an equality, most likely you end up proving an inequality. Proving an inequality instead of an equality. This is perhaps a little bit unnatural for beginners in analysis, because if you come from calculus or linear algebra, proving equality is usually achieved by manipulating existing equalities. But for analysis, what we usually do is use inequality arguments. This is way more common than manipulating existing equalities. Think about proving a limit statement. Think about proving a limit statement of a function. What do? You typically use an epsilon delta argument. These are inequality arguments. So here we have one equality, T plus A, outer measure less than or equal to A outer measure. And then we're just going to use a symmetry, sorry, not a symmetry, but apply this previous result. Apply this previous result, and to prove A outer measure is less than or equal to T plus A outer measure. So how do we do so? Well, we can write A equals minus T plus A, and then apply the previous result in which T is substituted by minus T and A is substituted by T plus A. Okay, so therefore we have minus T plus A outer measure. Are you a professor? No, not in real life. Less than or equal to T plus A outer measure. Okay, so this gives us what we wanted. Okay, so let's write that up as an exercise. I mean, mostly just a paraphrase, but we wish to do so in our own language. Okay, just make sure we understand all the definitions. This is definition. T plus A is defined as the set of T plus little a, where A is in big A. This is our proposition, and here's the proof. Okay, by the definition of outer measure, let I1 all the way to I1, I2 all the way be open intervals that covers A. Where can I find a PDF of this book? Is you just Google Axler, okay, just let me just put the link here in chat, okay. So because of the DMCA thing, everything I stream has to be open source, or why do we only, I'll answer that question very soon. So Axler measure theory, I'll give the link in chat, okay. It's completely free and it's legal, okay, including the supplement, and please make sure to download the supplement as well. Okay, so yeah, Countable, let's answer your question. So what do we just manage to prove in the in this paragraph? Okay, what do we manage to prove in this paragraph? In this paragraph, what we proved is for every set A, every subset of real A, okay, and every real T, we have this inequality: T plus A outer measure less than or equal to A outer measure. Because this is arbitrary. Everything here, T is an arbitrary real, and A is an arbitrary subset of reals. Okay, and because we have this identity, you have measure theory exams in 1.5 months. Wow, I don't know if I can help you in that short amount of time, because in 1.5 months we can have like 6 streams or something. I don't think I can even finish the first chapter. So, but good luck to you. Okay, this is not an exam review session. This is more like a seminar. So we try to build a solid foundation, and the goal is to be able to reconstruct the theory on our own. Okay, that's always the goal. I mean, something we should strive for. I mean, I tend to strive for, but your goal might vary. Okay, but that's my standard of learning a subject. Right? So if I'm learning a new subject, I try to strive for the ability to reconstruct the theory from scratch. Okay, so here what we're just saying is, because T is arbitrary and A is arbitrary, you can substitute to whatever you like to suit your purpose. Because we have this identity, you substitute T equals minus T and A equals T plus A. This way you just get A on the left hand side, which is exactly what you wanted. Okay, so the new A is T plus A, so that's exactly what you wanted. Okay. All right, so let's write that out ourselves. Mostly it's the same, but it's still good practice. So we have this inequality, okay? And then note of the union over K, T plus IK, contains T plus A. Contains T plus A. Let's just do a quick justification. To see this, let T plus A be in T plus big A for some A in big A. Right? Because T plus big A contains elements of the form T plus little a, where A is in big A. So this is an arbitrary element in T plus big A. Okay. Since A is in big A, it is covered by the open intervals. So A belongs to the union over KIK. That is to say, A belongs to IK for some K, for some natural number K, okay, for some K. Okay, so A belongs to IK for some K, then by the definition of shifting, right? So T plus A must belong to T plus IK by the definition of shifting. So therefore, we started from an arbitrary element T plus A in the right-hand side, and we showed that it is also a member of T plus IK. And by the definition of union, if it belongs to one of the set, it belongs to the union of those sets. Therefore, t plus a is belongs to the union. So this is something that is went over. That is something that only stated in the text. I mean, it's quite trivial, but let's prove it just to make sure we understand the meaning of countable union and shifting. Okay, so this is therefore we have this inclusion here. So we have this inclusion, and therefore let's call this star by star. Okay, let's say hence star. And star. Okay. All right. So. Okay. So by star we have the outer measure of t plus a less than or equal to the sum of the length of t plus ik over k. And since we have a property, the length of I equals the length of t plus, just use a different letter, t prime plus I, for all open interval I, and for all t prime in real, we have, it follows that t plus a absolute value is less than or equal to, or should we say, okay, just write the sum. Okay, the sum over k, the length of t plus ik is equals the sum of L of ik. Okay. Once again, very straightforward. Now, so we wish to break down a long proof into these super obvious steps. Okay. Okay. So anyway, this is what we have. And so overall, what we managed to show is we have shown for all open intervals for all not all open intervals should be the more precise way of phrasing that should be for all sequences, for every sequence of open intervals, for any sequence of open intervals of I1 all the way to I1, I2 all the way, such that the union of ik contains a, we have t plus a outer measure less than or equal to the sum of lik. Okay, so we have this relation. And as a result, by taking the infimum, right, so this means that t plus a outer measure is a lower bound of the set of possible sums for the length lik. Okay, so this is one lower bound. So it must be less than or equal to the infimum. So t plus a is less than or equal to the infimum of the sum of k lik, where ik are open intervals such that the union of ik contains a. And this is, of course, the definition of the outer measure of a. Okay, this is by the definition of our outer measure of A. Okay, so this is what we managed to show. Therefore, let's conclude that for all subset A of real, and for all t plus A absolute value, no, not absolute value, outer measure is less than or equal to A outer measure. And now you substitute t to minus t and A to t plus A. Note that t plus minus t plus A is just A itself. This is a trivial identity. You can verify it if you like. Just verify the double containment. Note that therefore minus t plus A. Okay, this is the outer measure of A. Is less than or equal to t plus A outer measure. So overall, the two are the same. Outer measure is translation invariant, i.e. outer measure is translation invariant. Okay, I apologize for the chicken scratch, the horrible handwriting. Hopefully this is readable. Okay, if you have trouble reading my handwriting, please let me know in the comment. Okay. So, all right. So let's take a look at the next proposition. Well, here's a comment. It says the union of the intervals 1, 4 to 3, 5 and 3, 5. Okay, let's draw the picture just on the side. This is 1, 4 and 3 is here. 3 is here, 5 is here. Okay, 1, 4 obviously has length of 3 and 3 to 5 obviously has length of 2. Right, so here we have an overlap. So therefore, the union of 1, 4 and 3, 5 is 4, while the sum of the right-hand side is 5. Right? So therefore, this inequality holds. The direction of the inequality above is explained by noting that the interval 3, 4, which is the intersection of 1, 4 and 3, 5, has its length counted twice exactly. The overlapping portion 3 to 5, 3 to 4 is counted twice on the right hand side. Okay, that's very intuitive. The example of the paragraph above should provide intuition for the direction of the inequality in the next result. The property of satisfying this inequality in the result below is called countable subadditivity. Okay, countable subadditivity because it applies to sequences of subsets. Okay, so here's the proposition. Countable subadditivity of outer measure. Here it says, suppose A1, A2, all the way is a sequence of subsets of real. Then we have this inequality. Basically, the outer measure of the unions of AK is bounded above by the sum of the outer measures of AK. So basically, if you want to bring the outer measure sign inside, well, you change the union sign to the summation and then have this inequality. Let's see how this is proved, and we'll try to reproduce it, or perhaps just summarize its basic ideas. Okay, it's to see. The key is always to see whether there's something that seems unnatural. There's something that seems unable. We are unable to come up with on our own. Okay, so that's a great way to collect ideas, because let's be honest, right? Sometimes the proofs in real analysis can be highly non-intuitive. So if we can identify points that seem unnatural, we're likely to pick up new tricks in our arsenals. Okay. But however, most important of all is the overarching idea of the proof. Okay, not specific tricks. Okay, so first we have a trivial case being taken care of, namely if one of the sets in the sequence has infinite outer measure, then the inequality above clearly holds. Because if you have one set whose outer measure is infinite, that means on the right hand side there's a term equals infinity. So automatically the right hand side equals infinity. Remember, the sum on the right hand side is a sum of non-negatives. Right, so if one term is infinite, then the whole sum is infinite. And if the whole sum is infinite, it doesn't matter what the left hand side is, the inequality always holds. So that's a trivial case. Therefore, we assume all AKs have an outer measure, have finite outer measure. So basically, that's the case we focus on. So how do we cook up the argument? Does it look like we're abusing the Zeno's paradox again? Does it look like we're abusing that Zeno's paradox again? So here it says, let epsilon be positive for each k in z plus. So basically that's positive integers or natural numbers, 1, 2, 3, and so on. Let I1k, I2k, blah, 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 be a sequence of open intervals whose union contains ak. Okay, so for each k, we're selecting a sequence of open intervals that covers ak. Okay, so that means the total length of all these open intervals, I1k, I2k, and so on, their total length should be greater or equal to the outer measure of ak. Right, so that should be the outer measure of ak. And what we're doing here is something interesting. So we know this is the sum for we're summing over the first index. Right? We're fixing k, summing over the first index. So that's the total length of this sequence we just talked about. Why is this less than or equal to epsilon over 2 to the k plus ak? Why is that? Well, this has something to do with the definition of infimum. Remember, the outer measure is defined as an infimum. Let's just briefly recall the definition of infimum. Is it here in the appendix? We have the definition of supremum. Perhaps it has the infimum as well. Yeah, definition of infimum. Oh, hang on. Infimum is the greatest lower bound. Yeah, this is an infimum. So imagine you have a set A. Once again, not necessarily an interval. That's a set A of reals. A number B is called the greatest lower bound of A if the following conditions hold. First of all, it needs to be a lower bound. Right? It's the greatest lower bound. It first needs to be a lower bound. Okay, so B has to be here. It is also the greatest lower bound, meaning for every lower bound C of A, C is less than or equal to B. Okay, so anything that is greater than b will fail to be a lower bound. Does it make sense? So imagine if you move c to here, there's going to be certain elements in a that is less than c. So this way c fails to be a lower bound. So therefore the second bullet point, hi Versky. So the second bullet point can be not paraphrased, but can be equivalently stated as follows. For every epsilon greater than 0, b plus epsilon is not a lower bound, is not a LB of A, is not a lower bound of A. So coming back to this statement here, we know AK is what? AK is the least greatest lower bound, the infimum of the set of sums, sum of L of I, J, K, where K is treated as fixed for now, and the sum is over J. And there's a bunch of conditions, you know what I mean. The union of I, J, K needs to cover AK, and they have to be open intervals. Because AK is the infimum, so everything, hang on, yeah, so since AK is hang on, there should be a absolute value sign here. That's the outer measure. Okay, AK is the set. Okay, what I just wrote without the two vertical dashes is not valid. Okay, so this is correct. Outer measure is an infimum. So by adding a positive, George Peng, I think it was you who made a comment at some point that you wanted videos on measure theory. Is that you, George? If so, this stream is made for you. So here, I was talking about AK outer measure being an infimum. So by adding a positive to that, it would fail to be the infimum of this set. It is not a lower bound. So it would fail to be a lower bound of this set. It will fail to be a lower bound of this set. So that means you can pick a set. You can find a smaller sum, basically. You can find a sum that is less than or equal to. You can find the sum that is less than or equal to epsilon over 2 to the k plus AK outer measure. So this is just an application of the definition of infimum. Since outer measure is infimum, if we add that by a small number, it will fail to be an infimum. What does it mean that it will fail to be infimum? Well, it will fail to be a lower bound. What does it mean it would fail to be a lower bound? It means you can find a sum that is less than that. Okay, so that's this statement. Okay, and then you're just going to, as I was talking about, you're going to abuse the Zeno's paradox. The choice of epsilon over 2 to the k is highly deliberate. So by summing over k, the first term on the right hand side is the sum of a geometric series, which is epsilon. And on the right hand side is something that we wanted in the original statement, the sum of the outer measures of AK. All right, so what we want to do is to somehow connect the left hand side, this double sum, with the outer measure of the union of AK. Right, so that's what we wanted. So we wanted to connect what we have on the right hand side, on what we have on the left hand side, namely 2.9, with this thing. Let's see how that's done. The doubly indexed collection of open intervals, ijk, remember, k here, k refers to the subscript of ak. Right. For each fixed k, ijk's, all ijk where you vary j, in which you vary j, covers ak. So remember the meaning of this. Can be rearranged. So this is perhaps a trick, right? So we're going to rearrange into a sequence of open intervals whose union contains the union of all the AKs. Okay, so these things are getting a little bit convoluted now. So now we're considering the unions of the AKs. So how do we argue that? How do we argue that the totality of all those IJKs covers the union of AK? As follows. Okay, where in step K, okay, starting with K equals 2. Why not 1? But let's just keep reading. Starting with K equals 2, then K equals 3, 4, 5, and so on. We adjoin the K minus 1 intervals whose indices add up to K. Okay, so I11, let's call it the sum of indices is 2. I12, I21 is 3. Right? The indices sum up to 3. Right? So I13, I22, I31, they have index sum being 4, and so on. Okay. So what are we doing here? The inequality 2.9, this one, which we just justified, inequality 2.9 shows that the sum of the lengths of the intervals listed above is less than or equal to epsilon plus the sum of AK outer measure. K goes from 1 to infinity. Why? Why is that? Well, let's do some scratch work here. So A1 covered by I11, I12, I13, and so on. A2 covered by, right, the set covered by. A2 is covered by I21, I22, I23, and so on. A3 is covered by I31, I32, and I33. So this way of listing the intervals IJK is a diagonal arc. Seems like a diagonal arrangement, right? Okay, on this, so the diagonals along this direction would have constant index sums. Index sums 2, index sums 3, index sums 4, and so on. So what is the advantage of doing that? Inequality says inequality 2.9, which is this one. It says the total sum of the lengths of the total, the sum of the total lengths, basically, right? All those open intervals having their length being added together is less than or equal to epsilon plus the sum of the outer measures of AK. That's 2.9. We know where that comes from. It says 2.9 shows that the sum of the lengths of the intervals listed above is less than or equal to. Yes, that's right. But what is that? Why it has to do with this arrangement, though? Indeed, the sum of the intervals intervals listed above. Oh, okay. Listed above here. This is a list. You're just writing it in a different way, right? So, in the original way, you first fix K and then you sum over J, and then you sum over K. But here, the order of the summation is essentially changed. The order of the summation is changed, which which on that requires a result. Why? Because in general you cannot always change the order of summation. The original 2.9, 2.9 here, the order of the summation is as follows. So you sum up every row, and you get a sequence indexed by k, and then you sum over those two. So add up the first row, second row, and blah blah blah. So here we're doing in a different order. You're summing things diagonally, and this does not change the result of the sum because each term is positive, not or non-negative. Now, each term is non-negative. So switching the order of, or should we say, changing, by switching the order, I don't mean just change I and j, okay? You can use any rearrangement. I think this is a theorem in Baby-Rudin for a non-negative series, provided it converge. Okay, you can sum whichever way you like. Okay, so can be rearranged into a sequence of open intervals whose union contains. Yeah, sorry, we read that part. We read that part. Okay, so the union of AKs, the union. Hang on, I'm still struggling to see why this arrangement is necessary. If it's converted, it's absolutely converted as well. Exactly, that's the reason. Yeah, that's the reason you can swap the order. But basically, here, why are we doing this rearrangement here? Because it seems like we aren't being. Hang on, the union of AK. The union of AK has. Instead of summing by squares, you sum by triangles, exactly as you drew it. You can do that if the doubles. Yes, exactly. That's the reason. But why do that though? Why do we bother though? That's I'm trying to figure out. So the whole objective right now is to connect 2.9 to this, right? So we want to connect the left-hand side of 2.9 to the union, to the outer measure of the union of AK. How is that relevant now? Well, the union of AK is union. Let's treat that as a single set. Okay, let's treat that as a single set. The union of AK is covered by these intervals, I suppose. Are these intervals? No, they aren't intervals. But okay, each of them is an interval. But I thought they were Sheldon Axler is union is taking the union of say I12 and I21. No? I do not see why yet either, right? So this is a little bit odd. Why do we need this? Okay, let's keep reading because okay, this is. I mean, of course, if you have this, then the next thing follows. Right? Because if epsilon is arbitrary, then you do have that. So, but why is this necessary though? Well, why do we need this arrangement to? Let's look at what it says. The doubly indexed collection of the open intervals can be rearranged into a sequence of open intervals whose union contains as follows. We want that to be a sequence. So we want that to be a sequence, right? Remember, in the definition of the outer measure, right? Basically, you don't want to have a. I mean, it's mostly. I think it's not a huge point, because in the definition, we need a sequence. But here we have a double sequence. Here just saying that the double sequence can be rearranged into a sequence. And you essentially use the Cantor's diagonal element, a diagonal argument. Remember the classic proof in elementary real analysis that the rational numbers are countable? You do this thing, this zigzag thing, right, to prove the rational is countable. Right? So basically, it's just a way of saying that the open intervals ijk can be rearranged into a sequence, into a one-dimensional sequence, not a 2D sequence. Right. So because here what exactly does the adjoining the interval mean here? You're not adjoining. Adjoining. I don't think they're taking the union because the union is not necessarily interval. It's just a way to write this enumerate. Okay, it's just a way to enumerate the open interval. So I think this part is perhaps a little bit unnecessarily complicated. Right? So basically, actually just saying that the double here, this is the sentence that what we mean here. So the double index collection of open intervals, the family of ijk, can be rearranged into a sequence of open intervals whose union contains. So basically, it says the union of ijk, okay, contains the union of ak. Okay, contains the union of ak. So that's I think we're okay with that. Because we want to write this as a union of sequence. Yeah, that's my thought as well. So the convex hull of the intervals. I don't think that's the convex hull either, because convex hull you're taking convex combination. So this is, I mean, I think this is perhaps a little bit unnecessarily complicated. Basically, what we're doing here is just this diagonalization, not diagonalization, but diagonal element, diagonal argument, my bad, diagonal argument of rewriting a double sequence into a single sequence. It's just a matter of writing the double sequence into a single sequence. And of course, because each row in this table covers one AK, right? And you can, by taking the union of all the ijk's, it covers the union of AK. It covers the union of AK. So that's the whole point. So you're basically you want to write this union as a union of a one-dimensional sequence. That makes sense. It's just turning a double sequence into a single sequence. Exactly. That's a requirement of the definition. Unions are not intervals. Exactly. It's not. We're not taking, say, union of I12 and I11. No, this is a sequence. You see here, Sheldon Axler says it can be rearranged into a sequence. This is a sequence of open intervals. So now you can just say this is. Let's give it a different name. Let's just say this is J1. This is J2, J3, and so on. That's a sequence. So the union of IK is the union of JK. That's it. It's just it's quite uninteresting actually. There's nothing super deep going on. It's just a matter of turning a double sequence into a single sequence. All right. So that's it. Okay. All right. I think it's fair that we'll just state the result and then comment on the main idea. Okay. So the result says the proposition outer measure is countably subadditive. At A1, A2, blah blah blah. Yeah, it's simpler than it seems, exactly. So be a sequence, of subsets of reals. Okay, then the union of AK, taking out a measure, is no greater than the sum of AK. Okay, so here's the main idea of the proof. Let's write the sketch. Yeah, it's basically exactly Christian. I was just talking about that. Yeah, this I was talking about the cardinality of the rational um, equals the cardinality. Yeah, yeah, that's exactly right. Um, it's turning a double sequence into a single sequence. Proof sketch. First, assume AK outer measure to be finite for all k to avoid triviality. So that's what we're dealing with. So for each k, there exists, let epsilon be positive. For each k, there exist open intervals I 1k, I 2k, and so on, such that because we want the sum of sum of AK to be on the right hand side, so we want to construct we want to put the sum of AIK on the right. That's the idea, I think. The sum of AIK outer measure, we wanted to put it on the right. Oh, actually, it's just AK. Let's put AK outer measure on the right. Epsilon over 2 to the k. This is greater or equal to the sum over j, the length of I, j, k. Okay, and then immediately sum over k. This is abusing the Zeno's paradox, as I was saying. Right, just see the proof for A outer measure equals 0 if A countable. It's the same trick. So be prepared to use this a lot. Okay, so we have that, and then we can just comment on, we turn the left hand side. We're going to turn the left hand side into, can convert the left hand side to not converting the left hand side. So basically the idea is turn the double sequence ijk into a single sequence. Because this is a requirement of the definition. of the definition of the outer measure. Can you please elaborate a little bit where exactly do you use the Zeno's paradox? So this is the Zeno's paradox. The Zeno's paradox is I was using this geometric sum, right? Because the geometric sum is related to the Zeno's paradox, or you can just we can rephrase that as saying we're using the geometric series. We're using the geometric series to construct an arbitrary small gap between the left hand side and right hand side. Okay. I think abusing, quote unquote, the term abusing Zeno's paradox was first coined by Terence Tao. So it's just, remember in the proof, I was talking about it earlier, I remember in the proof of, right here, that, hang on, the countable set has, the countable set has zero outer measure. We did the same thing. Andre, we did the same thing here. That's basically it. Okay, so let's continue writing. The idea is to turn a double sequence into a single sequence, a requirement of the definition of outer measure. Yeah, which is the kind of a cheap calculus resolution to Zeno's paradox. Right, so that's the idea. Using this can be done with, for example, Cantor's diagonal element, Cantor's diagonal argument. Well, Leo lecture is here. Tao has a blog post on standard tricks you would get through basically all of the standard analysis course. I kind of want to make that for other few courses, etc. Thank you very much for mentioning. Yeah. So this can be done with, for example, Cantor's diagonal element, diagonal argument, right? So here, this is the idea. And once that's done, we can say, we can claim the union. Let's just call it this the union of K, AK, is contained in the union of IJK. I will link it, but YouTube is stingy with links. Well, there are a lot of algebra proofs that could summarize with the algebraic geometry perspective. Okay, so yeah, that's the claim, and therefore, as a result, okay, check this. I'm not going to write a formal argument, but basically, if you fix k, let's say if we fix 1, and if we fix 1, so to prove this, you just need to show that every ak is contained in the union on the right. But this is obvious, right? Every ak is contained by, well, one row. So obviously it's contained by the union of the whole table. So, well, I'm just going to leave the details here. So as a result, we're using monotonicity. Actually, we're not using monotonicity. It's just actually we are using monotonicity length. So that's monotonicity of the outer measure. Actually, that's not auto. No, that's not. Hang on, that's not monotone. It's just a definition of outer measure. It's not monotonicity. It's just a definition of outer measure, because um, the right hand side here, this right hand side is not necessarily an outer measure for this. It could be made more efficient. Right? The covering could be made more efficient. This is simply just a definition of outer measure. Right. So that's what we have, and as a result, so you have the union of AK outer measure less than or equal to epsilon plus the sum of AK outer measure. Okay, and since epsilon is arbitrary, the union of AK outer measure is bounded by the sum of the outer measures of AK, taking the sum. Okay. So that's the sketch of the proof. Okay, so yeah, exactly. I'm glad everybody is on board, hopefully. Okay, let's continue pushing. So here we have a Leo is very knowledgeable about so many different topics. My goodness, I should really check out more of your stuff. Everyone, go check out Leo's stream. Um, he's uh, he could use a few more subscribers, I believe. Right. So yeah, Leo is very knowledgeable. I've seen snippets of his live stream, and I really enjoy them. So go ahead and check out Leo's lecture. Okay. So let me just type in chat. Check out Leo's channel, everyone. And by the way, thank you, Christian. Because Christian recommended your channel to my Discord server. All right, so let's keep pushing. It says countable additivity implies finite subadditivity. So this is obvious because you can just let the subsets A1 to actually the subsets after AN to be all empty sets. So basically, that's a corollary for countable additivity. And in measure theory, we want countable additivity. We want countable additivity because this is the key feature that allows the interchanging of the limit operation. So you want to, for example, you want to interchange the limit operator and the integral. So that's the goal here. So to do that, you need countable additivity. So here, right now, it's a little bit difficult to see the importance of this property. Okay, countable subadditivity. What we actually want is countable additivity. We want the equal sign. I mean, the less than or equal to sign is good, but we actually want equal sign, and the equal sign is something that makes measure theory tick. Okay, but this is at least a step in the right direction. But I just want to briefly comment on one thing. Can we push a bit further? Can we push a bit further and want a argument, so to say? I want a result for uncountable collection. So imagine the left-hand side is now an uncountable collection of subsets. And you may wonder, okay, well, what is a uncountable sum? What is a sum of uncountably many terms? It can be defined. It can certainly be defined. So let me just write that, okay? So that's the this is the critical thinking component. So here, let's ask the question. Is uncountable subadditivity possible? Uncountable subadditivity. Question mark. And by that we mean the following. Let the collection of A alpha, where alpha is in J, in general, our solution for uncountable sum is integral. Here, I mean, of course, we don't want to touch the subject of integral, but I'm just going to use a definition that is that does not involve any integral. So, okay, let's say A alpha, where alpha is in J, is a collection. It's an arbitrary collection. It can be uncountably infinite. Some integral sum, I'll define that, okay? I'll define what uncountable sum is. It's an arbitrary collection. It's an arbitrary collection of subsets of real. Is the following true? Is the following true? So the outer measure of the union of A alpha over alpha, alpha is in J, in big J, is it less than or equal to the sum of alpha in J, the outer measure of A alpha? Is this true? And let's define this. Definition. For an arbitrary collection, for an arbitrary collection, say little a alpha, alpha in big J, of real numbers, of non-negatives, of non-negative real numbers. We define the sum of A alpha alpha in big J, right, to define this as the supremum of finite sums. We can define, right, where alpha is in big I, where I is a subset of J is and I is finite. And of course, this recovers the uncountable sum, namely infinite series, right, when J is indeed countable. Yeah, exactly, the non-negative, so that's why I added this assumption. But here we just need to care about non-negative, because the outer measure is non-negative. So is this true though? Right, so now we have defined uncountable sum. So uncountable sum doesn't always have to do with the integral, right? So we can define it as a supremum of finite sums. Supremum of finite sums, right? Supremum of sums whose indices are finite or in a finite set. So that's the idea. Right? We can define it. So, but is this true though? Can we push it a bit further? Let's still use the same definition of outer measure. Well, there's an obvious counterexample that fails to work. So let's consider the following. The answer is it fails. It fails. So we do not have uncountable subadditivity. And here's a counterexample. So how do we cook this up? Well, let's consider the fact that the open interval 0 to 1 is the union of the singleton of x, where x is in 0 to 1. So this is a uncountable union. This is an uncountable union, right? So obviously the union of x, where x is in 0 to 1, this is just the outer measure of 0 to 1. Actually, we're getting ahead of ourselves, but let's just use the fact that the outer measure of an interval 0 to 1 is indeed 1. Okay, this is equal to the length. This is something that is proved later. Okay, let me just give you a quick glimpse of that. Okay, so here it is proved. It is proved here in the text that the outer measure of a closed interval is indeed the length. Yeah, that actually needs to be proved. But here, why this is not? Why does it make a counterexample? Well, the sum of the singleton length, okay, the sum of the length of the singletons is 0. Okay, and for this is the left hand side, but for any finite subset of 0 to 1, any finite subset I contained in the open interval 0 to 1, the sum of x, the sum of the length of x, where x belongs to I, is just the sum of 0, which is 0. Because this is true for every finite subset, that taking the supremum will give you a 0. And therefore, the sup of the sum of x in I, x singleton outer measure, right. I is finite. Oh, sorry, my bad. Here it should be the open interval, not the set with 0 and 1. Okay, this should be the open interval. I finite is 0. The supremum of this set is 0. So therefore, you see, therefore, the union will have an outer measure that is greater than the sum, is greater than the uncountable sum. The sum of the outer measure. Yeah. Because the right hand side is 0, the left hand side is 1. So it fails. So this means countable additivity is what we can hope for. Uncountable additivity is too much. So here we have some controversy in chat, apparently. As you see it, countable additivity is the road to integrals. I think so. I think that's, I mean, of course, this is a very vague statement, right? Countable additivity is what makes the big integrals tick. Okay, countable additivity can be said that countable additivity is what makes the big integrals behave well under exchanging limiting operations. So that's the main motivation here. Okay, so I was reading a book by Real Analysis and Probability by Ash, which is a nice book, which I recommended in my video, Measure Theory Made Doable. Here I'm reading the physical book. I can't show it on stream, but basically that's what he says. Closure under countable union and intersection is difficult to justify physically, because that remark refers to the definition of sigma algebra. But basically, countable union is a huge interest. So even though here it's not clear why we're interested in this property, but basically he says perhaps the most convincing reason for requiring it is that a richer mathematical theory is obtained. Okay, so let's just take this for granted. Okay, let's just take it for granted that countable additivity, countable union, that sort of stuff, is what makes measure theory tick. Okay, of course that's a very vague statement, but hopefully we can, but not hopefully, but we will reveal the precise mechanism that is true. Okay, so this is a consequentialist. What do we mean by consequentialist? Are we talking about moral philosophy? Yeah, you never actually add up infinite numbers during the definition of Riemann integral. Okay? So in Riemann integrals, you're taking a finite sum, and then you're taking the collection of them. Right? So you're considering the collection of all those possible Riemann sums, and then you take the supremum, which is the lower Riemann integral, and then you take the infimum, which gives you the upper Riemann integral. Right? So that's the approach we discussed last time. So it's a typical bound squeezing argument. Right? So the lower sum and the upper sum are two finite sums. So they serve as a lower bound and an upper bound. So you try to push the lower bound to be as great as possible, and you push the upper bound to be as small as possible. Then hopefully the two will meet somewhere in the middle. So that's the idea. We take countable additivity because we get a richer mathematical theory out of it. Exactly, Leo. That's precisely the reason. So even though right now it's a little bit difficult to see why this is important, but basically that's the main objective. Remember, in our last stream, we did talk about the deficiencies of Riemann integrals, right? So Axler was pretty clear about that. That's one of the motivations for introducing the big integral. So basically, remember, because analysis relies heavily on limits, right? A good theory of integration should allow for interchange of limits and integrals, at least when the functions are appropriately bounded. Right? And the previous example points out a series deficiency in Riemann integration. So here we have an example. Its construction is based on the good old Dirichlet function. F of x equals 1 if x is rational, if f of x is 0 if x is irrational. Right? And you can construct a sequence of Riemann integrable functions whose pointwise limit is not Riemann integrable. And this is not good, right? We don't like that. We don't like that, and even though we do have some positive result, it still has problems. Okay? But we're not going to dive into that because that's already covered in the last stream. So this is already a good foreshadowing of why countable additivity is important, right? We wanted to essentially we want to approximate. We want to approximate a complicated set using less complicated set. Right? So what is that approximation? What is that approximation? So it's some sort of limit of a set. Right? So how do you take limit of a set? Well, you take countable unions. But why not uncountable union? Because, well, uncountable union would give us nonsense. Right? Uncountable union would not behave well. So countable union it is. Right? So to be fair, I use the Dirichlet function to see if I ban them or not. Well, ban people in chat based on the Dirichlet function? What do you mean? Okay, that's funny. But here, anyway, so let's come back to the main theory. So I think this is perhaps a good critical reflection, right? So we proved countable subadditivity for the outer measure, and then we also see why it is impossible to strengthen this result. Right, so I think that's a good discussion. So now let's continue. The countable subadditivity of outer measure, as proved above, adds to our list of nice properties enjoyed by outer measure. Okay, so this is nice. Everything seems reasonable so far. Okay, but now we're going to, here, the next subsection, I think, is that we're going to get into perhaps a nasty result. A nasty result that is, let's just scroll down a little bit. Okay, so just to have an idea where we're going. Yeah, actually here still, in this subsection, everything is still nice, but in the next subsection, we have a nasty result. Okay, this is something highly problematic. The outer measure is not additive. Okay, we're trying to get there. So basically, it says there exists disjoint subsets A and B of real such that the outer measure of the union is not the sum of the is not the sum of the outer measure. So basically, this is highly counterintuitive. This is why measure theory is so unnatural. One of the reasons that measure theory is so unnatural, because of the weirdness of the real line. Okay, yeah. Okay, and then notice each step you need bootstrap structure from the previous. Okay, so basically, if you have A and B that are disjoint, we would expect the union to have an outer measure that is equal to the sum of the outer measures, but apparently this is not the case. Okay, so this defies our geometric intuition, and the reason for that is because of the wildness of the real line. The real line is a highly intricate mathematical structure. The real line is, I will always say this. So the real line seems quite simple, seems completely innocuous. It's just a line, but there are so many weirdness. This is the whole reason that real analysis is difficult is because more difficult, say, than complex analysis, because the real line is very wild. You can have so many counterexamples, and here you will see a construction of such sets A and B, which at the end it will rely on the axiom of choice. Okay? But we're getting ahead of ourselves. So let's come back to the more basic stuff. Okay? So this is just what we're trying to get to. Okay? So seems like everything so far, right? We managed to prove subadditivity, countable subadditivity, which is nice. But it turns out that additivity fails. And that's a major disappointment. All right, so let's continue properly. Outer measure of closed bounded interval, aka AB, like this, A to B, square bracket on both sides. One more good property of outer measure is that, one more good property of outer measure that we should prove is that if A is less than B, then the outer measure of the closed interval A to B is B minus A. Oh, actually, sorry, I was talking about when I was doing this proof, when I was doing the counterexample, I was saying, this requires a result down the road. It doesn't. This is trivial. The open interval has an outer measure of its length is already baked into the definition. It's already baked into the definition of length and the definition of outer measure. Okay, so here you don't need the result proved here. This is the open interval because you can simply take the cover of open intervals to be 0 to 1 and all the sets after are empty sets. So you don't need any special results. It's just straight from the definition. Okay, you just add here. You don't need a result. One can argue it's the wildness of axiom of choice, yes, you can say that. You can say the wildness of axiom of choice, that's for sure. But there's still other weird, like pathological stuff that goes on in the real line that has nothing to do with axiom of choice, right? Yeah. So, like I was thinking about the Cantor set, right? You know the Cantor middle third set. I'm getting on a side tangent. It's really dangerous. I should come back really soon. So basically, you know the Cantor one third set. You punch out the middle third of 0, 1. You keep punching out what is left, and this set has this fractal structure that is super weird. Okay. On one hand, it has the length of 0. On the other hand, it is uncountably infinite. And you can define weird functions like this devil staircase. Okay. But anyway, we're getting way ahead of ourselves. So the weirdness of the real line is not just due to axiom of choice. That's my point. All right. So that's the main objective. So here we're interested in showing that the outer measure of a closed interval is b minus a. Okay. So here is just an inline proof. I guess this is an inline proof. At least inline proof of a part of the statement. So we want the outer measure of the closed interval a to b to be b minus a. So how do we go about doing so? Well, let's draw a picture here. A is here, b is here. Right? We want a covering. Right? To discuss outer measure, we want a covering of open intervals. So here we're choosing epsilon greater than 0. Then a minus epsilon and b plus epsilon. So that's an open interval that completely contains a to b. So a minus epsilon is a little bit less than a, and b plus epsilon is a little bit greater than b. Right, so this open interval alone covers the closed interval a to b, and for the rest of the sequence, just use empty sets. As this is a sequence of open intervals whose union contains the closed interval a to b, of course. Okay, so therefore, by the definition of outer measure, you have the outer measure of the closed interval a to b is less than or equal to b minus a plus 2 epsilon. And because this inequality holds for all epsilon greater than 0, we have the first direction of this equality. So we have one direction of this equality. The outer measure of a to b, closed interval, is less than or equal to b minus a. So this is very nice. Is the inequality in the other direction obviously true to you? Oh, this sounds very ominous. If so, think again. Because a proof of the inequality in the other direction requires the completeness of R is used in some form. So let's imagine, of course, the other direction refers to the inequality outer measure of a to b less than or equal to b minus a. Oh, sorry, greater or equal to. So how do we go about doing it? How do we show this is greater or equal to? If so, think again. Because a proof of the inequality in the other direction requires that the completeness of R is used in some form. For example, suppose R was a countable set, which is not true, but as we'll see, but the uncountability of R is not obvious. Okay, suppose R is a countable set, then we would have it being 0 by 2.4. Yeah, so if R is countable, right, if R is countable, then the set A to B, being a subset of R, must be countable too. So it will have a length of 0. So Axel is saying this direction. So basically, the outer measure of the closed interval A to B being strictly positive. Remember, b minus a is strictly positive. The fact that this is strictly positive depends on R is uncountable. But the uncountability of R is not obvious. Actually, Axler proved it later on. I swear I counted all the real numbers before. There's like a double. Yeah, that's but one can ditch the axiom of choice and have a theory of the big measure in which all subsets of R are measurable, so the specific weirdness. Really? Really? If you ditch the axiom of choice, hang on, we're getting ahead of ourselves, but Leo, if we ditch the axiom of choice, then the non-measurable set would not exist, right? So that's what you mean. I think I've seen a comment that the existence of non-measurable sets and the axiom of choice are actually equivalent. I never seen a proof for that, okay? I confess. Yeah, so if you do that, I guess you can indeed have a theory of the big measure in which all subsets of real are measurable, but there's going to be situations where you need axiom of choice. Say, you're not sure if that's true. Okay, that's fine. That's fine. Let's continue. Let's not be distracted. So here, the point is the reverse direction of the inequality is not obvious because it relies on the property of R being complete. Right? Because as it turns out that completeness of R, the completeness of R, remember what is completeness of R? That was the key result or axiom, depending on how you see it, we mentioned in the last stream. Okay, so the completeness axiom says is also known as the least upper bound property. Here, every non-empty set. No, hang on. Where's the completeness axiom? The upper bound property is a part of definition of R. For what? Yeah, completeness is a Dedekind cut. I don't want that. I just wanted to have a simple statement of completeness. Yeah, complete ordered field. An ordered field is called complete if every non-empty set of F has an upper bound that has a least upper bound. Okay, and every non-empty set of F, a ordered field, has an upper bound, has a least upper bound. That's the definition of complete ordered field. The completeness axiom states that R is complete. Yeah, existence of what about Dedekind slice? Yeah, it works. So if you're taking, if you can prove that the Dedekind cuts form a complete ordered field, thereby showing that there exists a complete ordered field. Right, so that's the idea. So, but for practical purposes, you can just take the completeness axiom as a starting point. Dedekind cut is for showing that the axioms are not mutually contradictory. Okay, so here what we're saying is the reverse direction depends on the completeness axiom. It has something to do with the least upper bound property and whatnot. Okay, whereas the other direction does not require such property. Thus, something deeper than you might suspect is going on with the ingredients needed to prove the reverse direction. Okay, so as it turns out, we need a compactness argument to do that. The following definition will be useful when we prove that the length of the open interval, the outer measure of the closed interval is greater or equal to b minus a. Okay, so here, let's go through those definitions. And this is what we're going about. We're going to essentially define compactness. This is something that should be covered in elementary analysis, but we're just going to do a review because this is actually one of the hardest concepts in elementary analysis. 2.10 definition. Open cover. Suppose A is contained in R. A is a subset of real. I feel like that will come out forever from now. Okay. Actually, this is a self-promotion. I have a video on compactness on my channel. I mean, it's a very long video. It's like nearly an hour long, just on the definition of compactness. Okay, so go check out that video. Actually, I think I proved in, I mean, in that video, I proved the Bolzano-Weierstrass and the fact that the closed interval is compact. Okay. Anyway, here, open cover. A collection scripted C of open sets of R is called an open cover of A if A is contained in the union of... Yeah, yeah, I think the internet got disconnected. Hi guys, can you hear me? Okay, bye Wendell. Thank you very much for joining the stream. Yeah, I think, yeah, I just went back. Can you guys hear me? So I just came back because the internet, I don't know, it's been happening a few times recently. Okay, let's recall the definition of open set. Definition. First, we need to define a neighborhood. Let A be a subset of real. A is open if for every x in A there exists epsilon greater than 0 such that x minus epsilon to x plus epsilon is contained in A. And the set x minus epsilon, x plus epsilon, which we write as b epsilon of x, is called an open neighborhood or open ball of x. Okay, so this is the definition of open set. Essentially, what it's saying is that every point in A has some wiggle room. Okay, here's a picture. So this is set A. Once again, it may not be an interval. Every point x has some wiggle room. Formally speaking, you have an open ball centered at x that is contained in A. Okay. Yeah, open ball. Yeah, exactly. So that's the definition of open set. And you can prove that an open ball is indeed open. Okay, so that's the definition of open set. And here we're saying that an open cover is a collection of open sets whose union contains a set A. Okay. A collection scripted C of open set of real is an open cover of A if A is a union of C. Just write it this way. So this is, yeah, guys, I disconnected again. My goodness. This is so annoying. All right. Am I back? I should be back. So say something in chat if anyone can hear me. I can see the chat message keep popping up. So does anybody hear me? I'm so sorry. This is beyond my control, but annoying as heck. Okay, I'm back. Yeah. So yeah, Leo lecture. I was because you mentioned why compactness matters so much, right? So a while ago I posted a quiz, basically asking which theorem in elementary real analysis does not require compactness. First one, intermediate value theorem. Second, mean value theorem. And third one, extreme value theorem. And the last one is Riemann integrals of continuous functions. Continuous functions are Riemann. Continuous functions over a closed intervals. Continuous functions over closed intervals are Riemann integrable. So those are the four options. Which one of them does not depend on compactness? Now that's the question. So I guess, that my entire motivation of that question was to highlight the importance of compactness. There's only one of them that does not depend on compactness. Right? And yeah, I'll just give the answer because that's how important it is, right? So the only one that does not depend on compactness is the intermediate value theorem. Everything else depends on compactness in some shape or form. All right, so yeah, I was talking about the definition of open set and open cover. So now let's come back here. Yeah, extreme value theorem is the most obvious one, but the mean value theorem also depends on that too. But the mean value theorem, because the mean value theorem is equivalent to the row theorem. The row theorem relies on the Fermat theorem. Right? Remember the row theorem here. The row theorem says if a differentiable function has equal value at the endpoint, there must be a point whose derivative is 0, right? But that requires the existence of extremum. So extreme value theorem sneaks in here. So row theorem sneaks in. Row theorem is equivalent to MVT. So that's why the mean value theorem also relies on compactness. And lastly, continuous functions over a closed interval is Riemann integrable, needs an important result, basically uniform continuity. Continuous function on a closed interval is uniform continuous, and that requires compactness. Exactly, EVT on derivative, that's why. Actually, EVT on the original function, EVT guarantees the existence of extrema, max or min. And then because the function is differentiable by Fermat's theorem, by the first order condition, you would have a 0 derivative somewhere. So that's how you got the row theorem. So EVT guarantees the existence of the extrema. So that's how compactness sneaks in here. Right? And of course, I was talking about the fact that the continuous function over a closed interval, closed and bounded interval, is Riemann integrable. That requires a result. The continuous function over a closed interval is uniformly continuous. You need compactness. Basically, you need the existence of a finite subcover to conclude for every epsilon there exists a fixed delta that works for all x in A. So that's where compactness come in. So even for such basic results, right, you see compactness is seemingly everywhere. Right? Even though it's not seemingly everywhere, it is everywhere, even though it is sometimes not obvious just from the statement themselves. So indeed, compactness is critical. So here, an open cover C of A is said to have a finite subcover of A if A is contained in the union of some finite list of sets in C. Okay, so this is one of the most seemingly magical statements. So highly non-intuitive, but basically an open cover of A is said to have a finite subcover of A if A is contained, or should I say A is, let's write it this way. So if the union of C prime contains A, where C prime is a subset of C and C prime is finite. Okay, so this is highly non-intuitive, but basically let's draw a picture here. So here I'm not using the real line because I'm just going to use the Venn diagram to visualize this, because it goes beyond the definition of compactness. Right? You can pretty much extend that. Right? You can definition of open sets, open cover, and all of that can be extended to general sets. So here, let's imagine this is a set A. An open cover looks something like this. This is an open cover. So you have a collection of open sets that, well, covers A. All right, see you, Leo. Thanks for joining the stream. So basically, this is what an open cover looks like. Right, so this is what an open covers look like, and this collection of open sets can be arbitrary. It can be finite, it can be countable, it can be uncountable. Here, of course, for visualization purpose, we can only draw finitely many sets. But in general, the open cover is a collection of open sets whose union contains A. Right? And that collection can be finite, can be countably infinite, or can be infinite. So open cover on its own can have arbitrary cardinality. But what do we mean by saying an open cover has a finite subcover? It means that a data compression exists. A data compression exists, meaning you can select finitely many members in an open cover that still covers A. So you can, this is like the skeleton crew of a ship. Right? So if your goal is simply to cover A, and you can select a finite subset of an open cover so that the resulting union still contains A, then we call it a finite subcover. And an open cover is said to have a finite subcover of A if you can, let's say, delete certain sets until you have a finite set, and you have a finite collection that still covers A. Right. So as I was saying in my compactness video, what is compactness? Compactness is essentially, you can think of it as a generalization of finiteness. In general, of course, compact sets are infinite, but it retains certain features of finite sets, which makes things easier to handle. So that's a very primitive intuition, but quite instructive. So the idea is for finite sets, if you have a cover for a finite set, you can always get a finite subcover. Why? Imagine you have a finite set, right? You can list all these elements, A1, A2, all the way to AN. Right? This is a finite set. And you have an open cover. And you have an open cover for that finite set. For finite set, you can always, from any open cover of a finite set, you can always extract a finite subcover. Why? Well, take the first element of the set A1. Right? So take the first element A1 of the set. Because it is covered, right, by the original cover, right? So you can pick a set. Right? Pick a set in the original cover and keep that in the list. And you move on to the second element and you pick a second set. So you do this until you scan through all the elements, A1, A2, all the way to AN. And in the end, you of course always get a finite collection of sets that still covers A. So for finite set, you can always, from an open cover and get a finite subcover. You can always do this. For infinite sets, obviously this cannot be done in general, but compactness guarantees you can always do that. In fact, that's the definition of compactness. Let me just put it down here. A compact set, A is compact. A is compact. That's the compactness in topology. A is compact if every open cover of A has a finite subcover. Okay. Right, think of this as a data compression principle. A is compact if every open cover of A has a finite subcover. No matter how you cover A, right, you can do it as inefficiently as you like, but at the end of the day, you can always extract a finite subcover from it. And that's the definition of compactness. Of course, some textbooks define compactness in terms of sequences, and that's also okay. For the set of reals, they're equivalent. There's also a definition called the subsequence version. So basically, a set is compact if every sequence in it contains a convergent subsequence. So that's a sequential compactness. In topology, we call it the sequential compactness. In general, compactness and sequential compactness are distinct objects, right? Distinct concepts. They don't imply each other, but for metric spaces, such as the real line, the two are the same. Okay, so we decided to work with the cover definition instead of the sequence definition for a reason that shall become apparent. Right? Remember, I remember like when I was talking about the definition of outer measure in the last stream, somebody immediately typed in chat, does it have something to do with compactness? In general, I believe so. Okay, I'll have to. My topology is getting rusty. Okay, Christian, my general topology is getting rusty, so I can't answer your question right now. But yeah, it's definitely worth checking the condition on when the two are equivalent. I only clearly remember they're equivalent in the metric space setting. Okay, so sorry about that. Here, the set is compact if every open set of A has a finite subcover. Okay, so let's keep reading Axler, and we will perhaps see some examples. Okay, if Axler does not provide examples of compactness, I will do so. Yeah, that's okay. We all have the room for improvement, as I was saying. Okay, open covers and finite subcovers. What's going on today? Sorry, guys. I think I'm back. Okay, I'm so sorry. This is unexpected, and I can't do much about it. Okay, so let's keep going. So here we have a so here we have an example of an open cover. So 1 to 3, 2 to 4, 3 to 5, and so on. So each subinterval has endpoints being integers, positive integers, and the length are all 2. So let's draw the picture. 1 to 3 is this. Okay, 2 to 4 is like this. 3 to 5 is like this. And 4 to 6 is like this. Okay, and it keeps going on forever to the right. Okay, so what happens is, of course, they cover the closed interval 2 to 5. And this is horrendously inefficient, of course. But you can select a finite subcover. It has a finite subcover. It has a finite subcover because you just need 4. 1 to 3, 2 to 4, 3 to 5, and 4 to 6. This will do the trick. So that's an example of an open cover that has a finite subcover. What's remarkable is that the interval, closed interval a to b, will always have this property. Namely, if you pick an arbitrary open cover, it will always have a finite subcover. And that's something that is not obvious from the start. So because the difficulty in seeing that is you have to consider an arbitrary open cover, which can be quite complicated. Right? The whole idea is that, as we're getting to, the Heine-Borel theorem